In this video, we are going to talk about how to perform a buckling analysis with MSC Nastran. This is ultimately what you want. The top of your bulk data file should be first configured for a statics analysis or SOL 101. You want some load cases for that statics analysis, and then you want to create a second set of subcases that perform the actual buckling analysis. So here, I have two load cases for this model. Now I need to add two additional subcases that are going to perform the buckling analysis. So how do we do that? So we are going to be using a tool called the SOL 200 web app. Let me go ahead and go to the home page just so you look and see what that web app looks like. So this is the home page. Here at the far right, we're going to be using something called the viewer. Now, if you want access to this web application, you can visit theengineeringlab.com. At the top right-hand corner, there is a link to a free trial of the pre-post web app. So you would click that and sign up for the free trial. Here, let's go ahead and take our finite element model. So here is the example we'll be working with today. And then let's go ahead and increase maybe the size of the arrows just so we see how big the boundary conditions are. Oh, that's too big. So let's go ahead and maybe use one. So you can see we fixed this beam, if you will, on the left. And then we apply two forces here. Each force is in a different load case. So let's go ahead and look at those load cases right now. Here at the left-hand side, we click on the pre button. This opens this new window. We'll navigate to the case control section, and here we'll go to the subcases section. So here we've already configured two load cases. We already run Nastran. We get static displacements and stresses, but now we have to build on top of this and perform a buckling analysis. So how do we do this? Let me do this. Let me move this to the side, or let me open the right side so you see what's going on in the bulk data file. Let's go to solution sequence and go to configure. Right now it's configured for SOL 101 or statics analysis. Let's change this to buckling. So we'll select SOL 105. Notice here on the right now it says SOL 105. And let me move this to the side. And let's now go to the case control section. Let's add two subcases. So we'll add a subcase 3 and a subcase 4. Let's go ahead and now modify these subcases 3 and 4 so it's ready to perform the buckling analysis. One thing we need for a buckling analysis, we need to specify the method to extracting the eigenvalues. The eigenvalues are going to be the load buckling factors or buckling load factors, BLFs. So we need to tell Nastran, how are we going to perform the eigenvalue analysis? How do we extract the eigenvalues? So to do this, we're going to define something called the EIGR entry. So here, let's go ahead and go to the bulk data section. Let's reset this and look for EIGR. Let's go here and create an entry. Let's go ahead and select the Lang-Shows method to perform the eigenvalue extraction. And let's go ahead and now put, let's see, number of values. I think it's 10. I'm just looking at my notes here, so don't think I'm doing this off of memory. Right, so we want at most 10 eigenvalues or 10 buckling loads. Factors rather. So if you turn on display descriptions, this is going to tell you that the ND field, the ND value, is the number of roots or eigenvalues that you extract. Here we want at most 10 eigenvalues or 10 buckling load factors. Okay, now we have to go back to the case control section. Let's go to the command section and look for method. Method is going to be a pointer. We're going to turn it on for subcase 3 and 4. So you notice here at the bottom right, let's go and take a step back. So here we have subcase 3 and 4. And then when we turn on the method command, now we have method listed there. Let's go to configure. Let's look for method here. Or you can look that the first row is method. Here we'll go ahead and say for the method, for the eigenvalue extraction, use that entry we created a moment ago, EIGR ID1. So now we're saying here, hey, we know we're doing a buckling analysis. We need to know the method for extracting the eigenvalues or the buckling load factors. We configure the eigenvalue entry to extract 10 eigenvalues. Here we're saying use that entry, eigenvalue entry 1. Okay, now what is there left to do? Let's go ahead and select the constraints for those subcases. So what we do here, we go to case control, loads and BCs, navigate, we click on SPC. Here we select that SPC and we assign it to subcase 3 and 4. Now, what about outputting the eigenvectors? That's already done for us. If we go to commands and look for displacement, you notice that the displacement command, maybe let's look here. The displacement command has been turned on for the above subcase level. So what this means is that every other subcase is going to look at that top displacement command, and it's also going to output the displacements. But for subcase 3 and 4, the displacements are not displacements. They're actually eigenvectors. So in Nastran terminology, we're using the one word displacement to output both displacements and eigenvectors. So just keep that in mind. Okay, so I think we're done there. Let's go ahead and now run this. Let's try and run this and see if we get results. Okay, so we're done with the run. Let's go to result files in F06. Let's look for eigenvalues. Oh, it seems like we're getting a lot of data here. So I typically don't like to output all this data. So let's go ahead and do this. Let's go to case control. Let's go to configure. Let's go ahead and reduce size of F06. If you've seen my other video, it'll make more sense as to what this bind does. So I recommend watching the other video. I think it's called How to Reduce the File Size of F06 Files. That talks about what this bind does. So a moment ago, I had all this data in the F06 file. I didn't need all that data. So I clicked that button. It suppressed a lot of that output. And then here, what I'm looking for is this table, real eigenvalues. So now I get one table. These, if you look at the radiance table, let me copy this actually. Let me copy this table to a notepad file. So let me move this here. This is a table. We have column mode number, extraction order, eigenvalue, the eigenvalue in radians, and then the eigenvalue in cycles. Here is our eigenvalue column. These are the buckling load factors. But is this for buckling or for subcase 3 or subcase 4? If you look in the F06 file, at the top right hand corner, there's a label. That says subcase 3. These are the, I think I forgot to do something here. I forgot to turn on one very important thing, the STATSUB command. Let me look here and look at what the eigenvalues are for subcase 4. I believe they're the same. Subcase 3 and 4. Oh, okay. Yeah, there's a big mistake here. I forgot to include the STATSUB command. So that would be this command here. So what happened here, let me explain what happened here. 2, and then we had a subcase 4 here. StatSub is very important. Always add it to your buckling subcases. Here I made a very big mistake. I did not include the StatSub commands. So what happened? Subcase 3 did perform the buckling analysis, but we do not know for which subcase it did the buckling analysis for. Does subcase 3 take the results from subcase 2 and perform the buckling analysis? Or does subcase 3 take the results from subcase 1 and perform the buckling analysis? We don't know that. So I made the mistake of not including that. So let's go back to select here and look for STATSUB. We'll add it to subcase 3 and 4. We'll go to configure, and here we'll search for STATSUB. Here we'll say for subcase 3, use the results from subcase 1. Take the results from subcase 1 in buckling, or take the results from subcase 1 and perform the buckling analysis. For subcase 4, take the results from subcase 2 and perform the buckling analysis. Subcase 1 and subcase 2 were the two original subcases that were performed during the statics analysis. Remember, this started with SOL 101. Now let's go to download and rerun this. And then we'll take a look at the F06 file in a moment. Okay, it took a little longer because now we're actually performing the buckling analysis for both load cases. So now let's go ahead and look for these tables, real eigenvalues. If we're lucky, we'll have two tables here. We do. Okay, perfect. If you do not get two tables, it might be that you have to download the full F06 file and then look at the F06 file on your desktop. So here, fortunately, the amount of output is not that big. We only show you the last 100 or 1,000 lines of the F06 file. So just in case it's truncated and you don't see those tables, you could look at the same data on the F06 that we downloaded. Okay, so let's do this now. Let's look at the real eigenvalue tables. Okay, so this is the first table. We'll copy that to Notepad. So here, and then we'll copy this other one. Other table, right? So here I'm copying the row that's the subcase 2. Go to zoom out. So we have these two tables, the buckling load factors or eigenvalues. At the top right, it tells you the subcase 3 and 4. We know that we use STATSUB in subcase 3. We said for the buckling analysis, you use the results from subcase 1. So that's what we did. Subcase 3 is a buckling analysis. We said take the results from subcase 1, which is a linear statics analysis, then perform the buckling analysis. For subcase 4, we said take the results from the statics analysis, subcase 2, and perform the buckling analysis. So these results are effectively the buckling analysis for subcase 3 / subcase 1. These are the buckling analysis results for subcase 4 / subcase 2. Now, let's talk about a few things. Let's look at the buckling shapes, if you will. So to do this, we need to do one thing. Here on the left, we have to turn on the H5 file. So we output the H5 file. So here, let's click on add HDF5 out. Let's go ahead and run the Nastran analysis. We'll go ahead and wait a moment for that to finish. And then it should open automatically. And then we should get the first buckling shape, if you will. One important thing to know when you look at the deformations, think about the scale factor. If you use 1, that gives you the literal unscaled buckling shape, if you will. If you want to scale it up, as an example, say you use something really small, 0.01, you can see the buckling shape is not really noticeable. You can adjust the scale factor so it's more pronounced, like you see here on the screen. But what I'm going to do, I'm going to use 1. And here we see what that buckling shape looks like. Maybe we'll use 2 for now. So here on the right, we get some information. Let's see if I do get... Oh, let's do this. Let's look at the F06 output. Right, so the first eigenvalue is negative 242. And so that's listed here in this value here. It's time or frequency or eigenvalue. That's what this means, time or frequency or eigenvalue. Since we know that subcase is a buckling analysis, we know we get eigenvalues / buckling load factors. So we know that this value is actually the eigenvalue. You notice that the eigenvalue is negative. Why is that happening? That basically means that if we reverse the load, let me do this. let me turn off one of the forces. Let me go back there. So right now we have this force acting on this beam, if you will. So if we go to the next buckling shape, let's go ahead and go to mode 2. So this is the second buckling shape. So this buckling shape makes sense. We have this load going in the positive y direction. We expect compression on the underside wall, so we expect buckling on the underside. Now, what happens if we reverse the load? So let's suppose, what's the load right now? Let's go ahead and turn this on. The load is 1,000. Suppose we take that load, so 1,000, and we multiply it by -1. What does that mean? We're effectively reversing the load. So when we reverse the load, when this load goes in the negative y direction, the buckling shape is going to be different. So if this arrow were going in the negative y direction, we get buckling on the top side because now the top wall is experiencing compression. So when you see a negative buckling load factor, that just means that you're reversing the loads. All of your loads are being multiplied by that buckling load factor. Actually, let's look at this. Let's copy that positive buckling load factor. So we have the force times the BLF or buckling load factor, and then we get our buckling load. So here, I forget what the units are with this, so bear with me. So we do this, and I worked in marketing a lot, and one thing marketing does, it kills your arithmetic skills. Units of force. So let's suppose this is in newtons as an example. So this is our buckling load. Now, what if it's a negative buckling load? What happens? So we still go through that same process, but this time our buckling load factor is negative. So remember here in this table, where's that table? I think it was this one, right? So here you see we get negative eigenvalues. So that's okay. You just take that negative eigenvalue, you plug it into this equation, and then you get negative 242,000 pounds, or newtons, sorry. And then that's our buckling load. So again, if it's a negative buckling load factor, that's okay. You just multiply all your loads by negative, and that's your buckling load factor. Essentially, you're reversing the load. If this was an aircraft wing, it's the same thing. If there was a person sitting at the tip of the wing, you could either get buckling on the underside, or if you reverse the load, you could get buckling on the top side. So that's what a negative buckling load factor means. Okay, say you want to prevent that negative buckling load factor from even being extracted during the analysis. If you go back to the pre-web app, remember that the eigenvalue entry was responsible for extracting the eigenvalues. So here we'll say that for F1, which is the lower bound on modes, we'll say, you know what, maybe start at 0. Don't give me any negative eigenvalues. Start at 0, give me maybe 0.5, 1, 2, 100, positive 100. Give me only positive eigenvalues or buckling load factors. So we change that to 0. Let's go to download and click upload PDF and immediately run. And we'll do two things here. We'll confirm the eigenvalues are positive. So let me go back to the F06 file and let's look here, real eigenvalues. And then I think I might have to read, okay, maybe I misread that. Let's go back to the bulk data entry section. Frequency range of interest. Let's go here. Estimate root. I think it's one of these settings that you use to control that. Okay, sorry about the pause. I had to take a quick look at the quick reference guide to figure out how to get only positive eigenvalues. So here in the F1 field, it's not 0.0. It's actually a value greater than 0. So 1.0 e negative 9. So let me do this, 1.12. So just a really small value. As long as it's greater than 0, that should give you positive eigenvalues. So let's go to download, rerun this, and then we'll take a look at the eigenvalues again. So there are multiple places where you can look at the eigenvalues. Here, when you're at this table, you could look at this column in the table, time, frequency, or eigenvalue. Before, you'll notice that we have both positive and negative eigenvalues, but now you see we only have positive eigenvalues. If you go back to the F06 output, here's our table for subcase 4. You notice that the eigenvalue column only has positive eigenvalues. So that's the way you can control whether or not you get negative eigenvalues. If F1 is blank, you will get negative eigenvalues if they are within the search region, if you will. If the value is 0.0, you might also get negative eigenvalues. If it's greater than 0, then this will force searching for only positive eigenvalues. Okay, now let's see what else is there. Right, let's talk about one last thing. So what happens when we scale our loads by this factor? So let's suppose we actually scale the original 1000 units of force by the buckling load factor. What is our new, if F equals 242 newtons, what is the new buckling load factor? And here I'll just tell you new BLF should be what, 1.0. So what happens when you're right on the edge of buckling? Well, the buckling factor should be 1. So there are a few ways to do this. You can go to the pre-web app. You can modify the actual force entry. So if you go to force, and then you go here, you can make that one 242. Right, so you could take that 242 and you could place it there. Or you could do the following. You could scale up the scale number for the load case. So if you go to loads and BCs, go to navigate, go to the load section, and here you could take the loads. Here, I believe we're doing this for subcase 1 / subcase 3. So here you could say, you know what? Multiply all the loads by 242. And let's go ahead and rerun the analysis. So I believe we should get 1.0 there. And then maybe we'll try that for -1 also. We'll try when the buckling load factor is -1. So let's go look at the results. And then that's subcase 4. Let's go and look for subcase 3. Okay, here. So let's go ahead and copy this table here. And look what's happened to the first eigenvalue. Remember, we took the load, we multiplied it by the buckling load factor. Then we went back to the analysis and we now use, we scaled it by that factor, 242. We're right on the edge of buckling. And now look at our new buckling load factor. It's 1. We're right on the edge of buckling. Now let's do this. Let's go ahead and work with the original eigenvalue entry. Let's configure it so it outputs negative eigenvalues. Let's use a negative buckling load factor, -242. And let's go to download and run. And what should we expect? We should expect a -1 as the buckling load factor. We should expect a -1 eigenvalue since we went through that whole multiplication a moment ago. Right, so here if we look at this column here on the right, time, frequency, or eigenvalue, we get -1. Let's go back to the pre and look in the F06. And let's copy this new table. So let's go ahead and jump to the next line maybe. Here you see we get -1. Because again, we went ahead, we scaled all of the loads with the respective buckling load factor. Then we reran the analysis, and now we're getting buckling load factors of 1. We're right on the edge of buckling. Here, just to remind you, we went here to the load assignment table. So here, force 1 is in subcase 1, force 2 is in subcase 2. But for subcase 1, we multiply all the loads in that column by negative 242 and positive 242. Okay, so that's how you perform a buckling analysis. I know buckling analysis can get pretty complicated, even though it's kind of simple. Hopefully this video did a lot to show you kind of what the procedure is like to perform your buckling analysis for multiple load cases. Now, my apologies that earlier in this video, I forgot to specify the STATSUB command. This is very important. This is critical for your buckling analysis. Here, what we did is we created two new subcases, subcase 3 and 4. For subcase 3, we said perform a buckling analysis by using the results from subcase 1. For the fourth subcase, we said perform the buckling analysis by using the results from subcase 2. So that was a very critical step that I forgot at the beginning of the video. I had some weird results, but then I went back, added the STATSUB commands, and then we were able to actually look at the buckling shapes, if you will. Okay, so I think that's pretty much at the end of the video. I don't know if I mentioned it, but if you want to use this web application, you can go to theengineeringlab.com and you can click on free trial and sign up the form for a free version of this tool. So that's pretty much the end of the video. And as always, thank you for watching.